This will be our review for our second test covering sections 6.1 through 6.6. The first problem here, pretty easy and straightforward, comes out of section 6.1, number 21 out of the book, the corresponding problem on my lab. It's asking us to consider a velocity function over the interval 0 to 4. And you're given the original position as -2, and we're supposed to determine the position function. Okay, so all I have to do is take the velocity function given, and we know that the integral of velocity with respect to time is the position. So I just integrate that, and I get 18t minus 2/3 t cubed, of course, plus the constant of integration. Now we remember that the constant of integration for a position function is just the original position. So this just takes the place of c. And we have our final answer of, I put mine in descending order, -2/3 t cubed plus 18t minus 2. So very, very, very easy first question there. On to the second question. Looking at it, it's asking us to determine the area of the shaded region bound by the parabola -x squared plus 10x and the parabola x squared minus 6x. Okay, so rather than just depending solely on the picture given, you really should find the limits of integration. It looks like it starts at x equals 0, and it's kind of hard to tell. We can tell it's between 5 and 10. Just to be sure, you should set your equations equal to one another. Whoops. When I did that, I had the -x squared plus 10x equals x squared minus 6x. I chose to move everything to the right-hand side, added x squared, subtracted 10x on both sides. And then once I got a 0 on the left, I factored the right-hand side. A 2x factored out of that. Left me factors of 2x and x minus 8. If we set 2x equal to 0, that gives us the solution x equals 0. If we set x minus 8 equal to 0, we get the solution x equals 8. So, of course, then we know the x values 0 and 8 are where this is intersecting. Now, it's also very clear here inside of this region that you have a very easily defined top function and bottom function throughout this entire integral. And so you can say, well, the top function is your negative parabola, and then your bottom function is your positive one. So that's exactly what I've done here. I said, well, the area is just from where the intersection begins to where it ends, 0 to 8, of the top function minus the bottom function. After that, we combine terms. -x squared minus x squared is -2x squared. 10x minus a -6x is plus 16x. When we integrate, we get our -2/3 x cubed plus 8x squared evaluated at your limits of integration of 0 to 8. Of course, when we evaluate this at 0, we just get a very boring 0 for the lower limit. The upper limit does give us some values. We have -2/3 times 8 cubed. That's -2/3 times 512. It gave me -1024 over 3. And then plus 8 cubed, which is your 512. I got a common denominator here between these first two, of course, and ended up with an answer of 512 over 3. I would prefer the fractional answer, but of course, if you give me a decimal answer, that's okay. 170.667 rounded or 170.6 repeating would also be absolutely fine. On to the next problem here. It's similar to the one preceding in that we're finding the area shaded between the curves, but this time you don't have a clear top function and bottom function. In this region, the linear function would be the top function and the root function would be your bottom. But notice after this intersection point, now the constant function y equals 4 is your top function, and your bottom function is still that root function. To make this an easier problem done with one integral, all we have to do is say, well, let's integrate with rectangles that start at the left and end at the right, because clearly throughout this entire shaded region, the red curve, which is your root curve, is to the right of your linear function to x equals y over 2. Now, if we do that, the height of each rectangle here is going to be a arbitrary change in the y-axis. And as we do a summation, those delta y's become infinitesimally small and become a dy, telling us that we need to integrate with respect to y. So I can say, well, okay, then this is the integral of the right function minus the left function, or I should say the right relation minus the left relation, from where the values begin, and clearly they're beginning at the origin at y equals 0, and they go up to the value y equals 4. So I integrate from 0 to 4 of right minus left. And again, we have to have those in terms of y because we're integrating with respect to y. When we integrate, we get our 2y to the 3 over 2 minus 1/4 y squared. Just like the last problem, when you evaluate this at 0, you get a 0. All of our answers come from when we evaluate at 4. In the first one, it'd be the square root of 4 is 2. 2 cubed is 8. 8 times 2 is 16. In the second one, we know 4 squared is 16 times 1/4 gave me a 4 there, and we're subtracting. 16 minus 4 gave me a final answer of 12. Pretty straightforward problem so far. Now, I think the ones that students will struggle with maybe the most are these volumes of solids of revolutions problem. I'm going to have one consistent curve for all of the problems, and it should be a very, very easy curve to graph just by factoring and setting each of your factors equal to 0. So anytime I give you a negative quadratic, and if you can factor it and set the factors equal to 0, you can say, well, okay, that's where it's going to touch the x-axis. In this case, 7x minus 2x squared factored to be x and 7 minus 2x. If you set x equal to 0, you get x equals 0. 7 minus 2x set equal to 0 gives you 2x is equal to 7, and x equals 3.5. So I knew that this was a parabola pointing downward with x-intercepts here at 0 and at 3.5. Then I also knew that I was revolving the region about the x-axis. So I can say, well, okay, I'm taking this region bound by this curve in the x-axis, revolving it about the x-axis. I went ahead and drew an arbitrary portion of that rotation here, an arbitrary slice. I can say, well, every slice that I could draw, whether it's here at the beginning, here at the end, or somewhere in the middle like this, they're all going to have this formula for the radius that's just the height of the curve. The radius of each slice of revolution is going to be 7x minus 2x squared. So then I can say the volume of each slice is pi r squared times its thickness, which is a change in x. Each slice is arbitrarily has delta x thickness. Now, this becomes an algebra problem in that when you have that pi r squared and your r is this function's formula, it's a binomial squared. I had to be careful with that. I wanted to go ahead and show the FOIL here just to make sure you see it's not just the first term squared and the last term squared. We would have 7x times 7x is 49x squared. Then you would have minus 14x squared and another minus 14x squared for a total of minus 23x. I should have said cubed. And then you have negative 2x squared times a negative 2x squared gives me plus 4x to the fourth. Okay, so I have the volume formula for one slice, pi r squared delta x. And then I can say, well, all right, then the volume of the entire rotated surface is going to be this from where it begins to where it ends inside of an integral. So pi times the integral from 0 to 3.5 of this formula I just found integrated with respect to x. The only thing I've done from here to here, of course, putting it inside of an integral and wrote it in descending order, integrated just with the power rule in the next step. And then when we evaluate, I just plugged this one in the calculator. So when I evaluate this function at 3.5, I got this fractional value. Of course, when we evaluate this function at 0, we're going to get a 0. So I said it's pi times the upper limit minus the lower limit, which just gives us pi times the upper limit. In this case, 16,807 pi over 240. It's a pretty cool answer there. I believe that's like 70 something pi. Now, and again, I would prefer the fractional answer. I think the decimal answer is 70 point something, and that would be okay. I would want it to 3 decimal places, but the fractional answer is always cleaner and better. For number 5, we know that this answer should be larger than the answer for number 4. We're still revolving this region about a horizontal axis, but the horizontal axis is down 5 units. So it's going to have more of a region to accumulate volume as it rotates around. Now, the problem with that, as it rotates around there, you are going to be hollowing out the inside curve. So this is where I've tried to draw it up here. Each of your slices is going to be a washer, where we're going to say the volume of that washer, the volume of each individual slice, is pi times the larger radius squared minus the smaller radius squared. That's the formula I've set up here, pi times R2 squared. I always call the larger radius R2. Well, R2 in this problem is your curve, which is 7x minus 2x squared, minus the axis of revolution, which is -5. But if you subtract a -5, then you're adding 5. So I can say the distance from the axis of revolution to the outer portion of the curve is this equation, -2x squared plus 7x plus 5. All I did is I wrote f of x in descending order and then subtracted a -5, adding 5 to it. Now, we subtract the smaller radius squared, and consistently, whether it's the very beginning, the very end, or where I have it drawn, the smaller radius is a consistent length of 5. It's just the distance from the x-axis to the axis of revolution, 5 units. So we get our function squared minus 5 squared. I squared out that function. It would give me 9 terms when I squared it all the way out. Now, the very last term I didn't write because the very last term would be 5 squared. That's going to cancel out with this 5 squared. But I still had the -2x squared times that trinomial plus the 7x times that trinomial plus the 5 times that trinomial minus the very last term. When I did that, it gave me this expression. And from here to here, all I've done is I've simplified down by gathering like terms. I had 4x to the 4th. I had 2x cubed terms for minus 28x. I had 3x squared terms, minus 10x squared plus 49x squared. Minus 10x squared gave me a plus 29x squared. I had 2 of the x to the first terms. I had 35x plus 35x for a total of plus 70x. Okay, now that's the volume for one slice. The volume of the entire rotated solid is going to be this formula, pi times the integral from where the slices would begin to where the slices would end, again 0 to 3.5, of that formula integrated with respect to x. All we have to do here is power rule on each of the terms, pretty straightforward. And just like last time, I plugged this into my calculator to evaluate it at 3.5. When I did, I got the nice fraction, well, ugly fraction, 51,107 over 240. The lower limit was again 0, so I didn't have to worry about that. So after that, all I had to do is remember to multiply my fraction I got by evaluating at 3.5 by the pi out in front of it to get to my final answer there. Now, for the next problem here, and I want to make a very stark comparison between The method I recommend you use anytime you're revolving about a horizontal axis of revolution, whether it's the x-axis or whether it's y equals 5, those are best done by slicing because it enables us to keep our integration in terms of x. But anytime you're revolving about a vertical axis of revolution, if I were to do slicing in here, the slices would have a thickness with respect to y, and it would make this problem extremely difficult. So slicing is not a good idea on problem 6 and 7. Shells should be the method that you choose anytime you revolve about a vertical axis of revolution. So I'm asking you to revolve about the y-axis. Again, I have the exact same region, the curve bounded by 7x minus 2x squared. So if I'm thinking about shells, I know that the area under this curve, I could put infinitely many rectangles in there. Instead of area, we're going to be thinking of this as volume by rotating each of these rectangles about the axis of revolution. When we do that, we can see that a cylindrical shell is going to be created for each one. Now, the way I like to think about that cylindrical shell is you could rip it apart, and every one of those shells that go around, they're just going to form a rectangular solid where the height of your rectangular solid is just your function, 7x minus 2x squared. The thickness of your rectangular solid is just the thickness you have in each rectangle, which is an arbitrary change in x. And then the length of your shell here, that's going to be the circumference of the revolution, which we know circumference formula is 2 pi r. Well, r in this case is the distance from the axis of revolution to any one of your rectangles that you're creating in there. Well, fortunately for us, by definition, the distance anything is from the y-axis is defined to be x. So I can say, oh, well, then r is x, so my length of this rectangular solid is 2 pi x. I bring that down to create the volume of my arbitrary shell, 2 pi x times my function times delta x. I had to distribute the x through here to simplify algebraically before I put it into the integral. Once I put it into the integral, we just think about where do we integrate to and from. Well, it's from where the region begins to where it ends. So just like the slicing problems, it begins and ends when x starts at 0 and goes to 3.5. So we integrate from 0 to 3.5 of this function. We do so by just power rule. So we get 1/2 x to the 4th plus 7 over 3 x cubed. Yet again, we're evaluating at 3.5, which I would just plug into the calculator. When I did that, plugged 3.5 into this, I got the fraction. And in fact, it was 2,401 over 96. I had to multiply by 2 after I did that, which it ended up creating that 96 denominator, simplifying down to a 48 denominator. We didn't have to worry about the lower limit of integration since all of this evaluated at 0 is 0. I get my final answer of 2,401 pi over 48. For number 7, instead of revolving about the y-axis, which is what we did here, now we're revolving about the axis x equals 10. Now remember what we said, anytime you're revolving about the y-axis, by definition, the distance anything is from the y-axis, it's defined to be x. So now when I ask you, what is the radius from the axis of revolution? You just say, well, okay, that's the distance from the axis of revolution to any value. Each of these rectangles are at a distance of x, whether it's here, here, over here, and this is as x goes from 0 to 3.5. So you could say, well, then your radius is going to be 10 minus x. The longest the radius would ever be is 10. That's when x is 0. The shortest the radius would ever be would be 6.5, and that's when x is at 3.5. So I can say, yeah, 10 minus x, that's going to account for all radial lengths throughout this problem. That's the only thing that changes from 6 to 7. Each rectangular solid is still going to have a height of 7x minus 2x squared. It's still going to have a thickness, arbitrary thickness of delta x that creates that. And then its length, that determines by the circumference of the revolution, is 2 pi r, 2 pi times 10 minus x. So notice the last problem and this problem, extremely similar. The only difference is that radius formula. And that's the only difference you'll ever have from a shell problem to a shell problem. So I can say, okay, all I have to do now is algebraically simplify. I distributed a 10 through that group, then I distributed a negative x through that group, and I got the resulting polynomial here. After that, I just combined my two x squared terms, and I said, well, this could be better written as 2x cubed minus 27x squared plus 70x in descending order. This would be the volume for one arbitrary shell. So the volume of the entire rotated surface is going to be 2 pi on the integral from 0 to 3.5. Again, it's only from where the region begins to where the region ends in terms of x. So 0 to 3.5 of this volume of a shell formula, and I should have a dx here. So let me fix that. That is not a delta x, that's a dx. Bad, John. So now we integrate this with respect to x, and when I do that, it's just power rule again. So you'll have x to the fourth over 2 minus 9x cubed plus 35x squared. Just like the other problems through here, I evaluated this on my calculator by plugging 3.5 in for x. When I did that, I multiplied that answer by 2 and got the fraction 3,773 over 16 times pi. And of course, yet again, just like all of these problems 4 through 7, the lower limit of integration can be ignored because when we plug 0 into this polynomial, we get a 0. Looking at the next problem here, we're moving on to our arc length section, which was section 6.5. Number 8 should be the easy arc length problem. 9 should be the trickier version of the arc length problem. In both formulas, we just say, well, the arc length formula, it's the integral from where the arc length summation begins to where it ends, in this case 0 to 67, of the square root of 1 plus the first derivative squared. So the first thing I did here is I took the first derivative of my function. 3 over 2 came down and multiplied 1/3 to give me 1/2, and then I subtracted 1 from the exponent. 3 over 2 minus 1 gave me the 1/2 exponent. So I have 1/2 x to the 1/2. We square that. When we square it, we get 1/4 x to the first power here. And so then I can plug that into my formula. When I do, I said, well, the square root is the same thing as the 1/2 power. So I have 1 plus 1/4 x raised to the 1/2 power integrated with respect to x. Then I knew I could integrate that. Any linear function raised to a power, we can say, is that same linear function raised to the power plus 1 power, so to the 3 over 2 power, divided by that new exponent, 3 over 2, and divided by the derivative of the inside. That's where that 1/4 came from. And then we evaluate from 0 to 67. What I did is I went ahead and said, well, in my denominator, I'd be dividing by 3 over 8. Dividing by 3 over 8 is the same thing as multiplying by 8/3. So I took 8/3 times this group that I'm evaluating from 0 to 67. When I evaluated at 67, it doesn't make for a nice answer. I would just have 4 over 4 plus 67 over 4. That gave me 71 over 4 raised to the 3 over 2 power. When we plug in a 0, hey, look, we finally get an answer when we plug in 0. When we plug in a 0, we're just going to get 1 plus 0 to the 3 over 2. That's 1 to the 3 over 2, which is just 1. So my upper limit minus my lower limit, I multiplied that by 8/3. And if you want to, and if I ask for an exact answer, which I didn't specifically say here, but this would be my exact answer, and I really wouldn't simplify it beyond that. When I entered this into my calculator to get the decimal approximation, I got to this value, which for this problem, I kind of prefer the decimal approximation since the exact value is kind of ugly. Looking at the next one, and please notice here, I did say exact answers only. So it's the same arc length type problem. I know I have to take the derivative of my function. Well, the derivative of 4 natural log of x is 4 over x. I thought of this as minus 1 over 32 x squared. The derivative of that is going to be minus 1/16 x to the first. That's where that came from. So now I said, all right, that's the derivative. Now I need to square that derivative. So you would have 4 over x times 4 over x. That gave me 16 over x squared. The middle two terms are both going to be 4 over x times a minus 1/16 x. The x's end up canceling each other out, and I get minus 4 over 16 minus 4 over 16, which gives me minus 8 over 16, reduces down to minus 1/2. The last term times the last term, a negative times a negative is a positive. 1/16 times 1/16 is 1 over 256. And of course, x times x gave me the x squared term. So this is that derivative squared. But now I knew that that would look pretty ugly trying to put it into my formula. So I wanted to simplify it out before I tried plugging to my arc length integral formula. When we add 1 to this derivative squared, it ends up just changing that minus 1/2 term to a plus 1/2 term in the middle of our 3-term polynomial. Then at that point, I realize, well, hey, my first term is still a perfect square. My last term is still a perfect square. The only thing that has changed is this minus became a plus. So this can and should be written as not the original group, but the original group with the plus sign in between, quantity squared. If you squared out this group, it would give you this 3-term expression back. But now this is so much more useful in this format because when I plug it into my integral, I can say, okay, 1 plus the first derivative squared can be written as 4 over x plus 1/16 x quantity squared. The nice thing about that is that's now inside of our square root inside the integral. So that square and square root cancel out, and it just gives us the integral of the expression inside of that group. So this becomes fairly easy to integrate. The integral of 4 over x takes me back to 4 natural log of x. The integral of 1 over 16th x gives me 1 over 16th x squared over 2, which gives me plus 1 over 32 x squared. We then evaluate that expression from 4 to 8. When I evaluated at 8, I got 4 natural log of 8 minus 1 over 32 times 64. That gave me 4 natural log of 8 plus 2 there for the first one. Subtract the lower limit, so I subtracted 4 natural log of 4, and then I would have plus 1 over 32 times 16. Well, it's 16 over 32. That gave me plus 1/2 there. Now, I wanted to go ahead and combine terms. I had 4 natural log of 8 minus 4 natural log of 4. That gave me 4 natural log of 8 over 4. Remember, whenever you condense logarithmic expressions, if they have the same coefficient, you can keep that coefficient. And the terms on the inside, when you subtract, I didn't mean for that to disappear. When you subtract, what's going to happen is they divide out. So you'd say, well, 4 natural log of 8 minus 4 natural log of 4 is 4 natural log of 8 over 4 with the condensing rules. That's just 4 natural log of 2. Could have you left the 2 natural logs terms out individually? You could have, but this looks better. Then this would be my 4 over 2 here. I have 4 over 2 minus 1 over 2 for 3 over 2. Final glorious answer there. For the last problem, this is a pretty short test here. We have to find the area of the surface generated when this square root function for x equals 5 to 8 is revolved about the x-axis. Okay, so surface area formula, similar to our arc length formula, it's going to be 2 pi on the integral from where it begins to where it ends, 5 to 8, of f of x, or in this case y, same thing as f of x, on the square root of 1 plus the first derivative squared. So I went ahead and I said, well, let's take the square root, sorry, let's go ahead and take the derivative of this expression, the derivative of 22x to the 1/2. The 1/2 came down in front and gave me 11x to the negative 1/2 when I took the derivative. Then we have to square that derivative. Well, 11 squared is 121. X to the negative 1/2 squared gave me x to the negative 1. So that's what gets plugged in here. So I can say, all right, my arc length formula, 2 pi on the integral of f of x on the square root of 1 plus the first derivative squared. The first derivative squared, 121 x to the negative 1. That's the same thing as 121 over x. Now, what I've done to simplify this is I said, let's go ahead and factor that 22 out. That's where the 44 pi came from in the next step. And then I distributed. This square root of x can distribute to both terms inside of this square root, and it's just going to give me the square root of x plus 121. Now, it's very similar to the last problem in that you say, well, at this point, I just have a linear function to the 1/2 power. When I integrate that, that becomes that linear function to the 3/2 power divided by that new exponent, 3/2. You would also divide by the derivative of the inside, but the derivative of the inside is 1, so that doesn't amount to anything. Now, I'm evaluating this function multiplied by the 44 over pi still from 5 to 8. When I plugged in an 8, I would just get 8 plus 121 is 129. I had 129 to the 3/2 power, which is an irrational number, so I'd rather leave it exact like that. When I plugged in a 5 for the lower limit, I had 126 to the 3/2 power that we're subtracting. You'll notice the 3/2 that was in the denominator, I just said, well, that's the same thing as multiplying by 2/3, which gave me 88 pi over 3 out in front times this irrational expression. So what I've done is I've kept my only rational version of this, the 88 over 3 out in front, times when I entered this irrational expression into my calculator, I got this. And then, of course, we have our pi. When I simplified that down, I had 1,490.481 pi. And then if you wanted, since it's irrational anyway, I could see somebody reasoning, you might as well just go ahead and multiply the pi through it, and it would give me that answer. Any of these answers, even this answer right here, all of them would be fine. This is about as far as you could take it if I ask for an exact answer, just because when you're evaluating these, you're just going to get to the decimal approximations after that point. All right, and that is the end of this second test review. Hopefully you think this is not bad at all. In the case that something doesn't make sense, please keep in mind you have these practice problems you can go back to in my lab and get more examples with them. And of course, you can always contact me at any point.